When you step onto a train, whether it's, your daily commute or maybe a high-speed trip cross-country, you're placing trust in this huge, complex system.
Yeah, an enormous amount of trust.
You just assume inherently that every single bit of it, from the software managing signals to the actual steel rails, the brakes, everything's been checked, tested, certified,
Yeah.
safe.
And, well, that trust, it doesn't just happen by magic. For the people running the railways, the engineers, the regulators, that confidence, it's earned. It's built on a massive, really structured system.
Which brings us to what we're diving into today, System Safety Assurance, or SSA.
Exactly, SSA.
This is the whole framework, the scaffolding, both technical and legal, that makes sure any change, and I mean any change, could be a new door handle, could be a whole new train control system, is actually safe. Safe to integrate, safe to operate, safe to maintain.
It's the proof you need. The mandated proof, really, before anyone in the public gets near that change.
What's really interesting, I think, is how this whole SSA thing is driven by a legal duty, a duty of care.
Absolutely. It brings us straight to the bedrock concept, the foundation for pretty much all modern rail safety law, SFARP.
Okay, SFARP. Let's unpack that one. Sounds a bit dry, maybe, but you're saying it carries huge legal weight.
Monumental weight. It stands for so far as is reasonably practicable.
So far as is reasonably practicable.
Yeah. And SFARP, well, it's the benchmark now for what safe actually means. It's not just about ticking compliance boxes or meeting minimum standards.
It's more active than that.
Much more. It's a proactive legal duty. It comes from national rail safety laws, but also broader WHS, work health and safety rules. Everyone involved, the operator, the designers, the manufacturers, the installers, they all share this duty.
A shared duty to do what exactly?
To eliminate any safety hazard you can reasonably foresee. And if you genuinely can't eliminate it,
then you minimize it.
You minimize it. SFARP, so far as is reasonably practicable.
So it's not just about calculating a risk, seeing it's low, and saying, okay, we're good.
Definitely not. You have to be able to show, to demonstrate, that you actively thought about every possible way to make that risk even lower, and you only dismiss those ways for good, justifiable reasons.
Reasons like cost, or maybe the technology just isn't there yet?
Precisely. It involves this critical cost-benefit analysis, but it's heavily weighted towards safety. You look at the risk, that's the likelihood of something happening and how bad it would be if it did.
Likelihood and consequence, yeah.
Right. And you weigh that against the cost, the availability, the knowledge required, how suitable different fixes or mitigations are. This is where engineers, well, they become kind of legal gatekeepers in a way.
Can you give us an example? Make it a bit more concrete. How does that weighing up work in practice?
Sure. Let's imagine you've got a new component.
Yeah.
Maybe it slightly reduces the risk of derailment. Just a tiny statistical improvement.
Right.
Installing it costs, say, $50,000. Plus, you need a 4-hour track closure, which is disruptive. You do the sums. The risk is already pretty low. Maybe you think it's acceptable.
Right.
But then another company comes out with a different component. It reduces the risk by the same small amount, but it only costs $500. And you can install it during normal maintenance, no extra closure needed.
Ah, okay. Much more practicable.
Exactly. Now, if you don't install that cheaper, easier, equally effective measure, even if the risk was already low, that failure is seen as negligent under SFER.
Wow. So you have to take the reasonably practicable step, even for small gains.
You have to demonstrate you considered all reasonably practicable precautions, not just the big expensive ones. And that's why SSA is so rigorous. It forces you to show you're working, to prove practicability.
Okay, so SFARP sets the standard. That's the goal. Now, how does SSA actually turn that legal duty into an engineering process? I think a common misconception is that SSA is just like a final checklist you do before flicking the switch.
Yeah, that's completely wrong. A very common mistake.
It misses the point.
Fundamentally, SSA isn't some final audit tacked on at the end.
Yeah.
It's most effective, and frankly, it's required when you apply it throughout the whole life cycle of a change.
From the very beginning.
From the initial concept idea, right through design, building it, testing it, verifying, validating, all the way. And for changes involving physical assets or complex systems, SSA has to link directly with systems engineering SE standards. Things like ISO 15288.
You can't really separate the technical design from the safety process then.
You can't. They have to be integrated. And that integration, well, that's often where you see friction on projects, isn't it?
I can imagine. Safety can't just be stuck in a corner office.
No, it needs to mesh seamlessly with design management, with RAM analysis, reliability, availability, maintainability.
And human factors too, right? HFI.
Critically, yes, human factors integration. And this is where, sometimes organizational politics can clash with the ideal process.
How so?
Well, a project manager, they're under pressure with deadlines, budget. They might see safety as maybe a necessary hurdle rather than a core part of the engineering itself.
Right, something to get through.
But if your RAM analysis flags a component with a high failure rate, that has to immediately trigger a safety reassessment. If your HFI work shows the control panel is confusing for drivers, that's a safety hazard. It needs fixing.
So SSA acts like a central governor, pulling everything together.
Exactly. It demands inputs from a really wide range of different sources, different contexts.
Okay, let's maybe list some of those key inputs. They really define the scope of the whole safety argument you need to build.
Yeah, good idea.
Obviously, we start with legislation and regulation.
Yeah, the specific rail safety laws in place, plus the general WHS or OHS requirements that protect workers doing the installation, the maintenance. But just complying isn't enough.
What else?
You have to look backwards. Historical data. That means digging into your own incident reports, near misses, but also looking globally. What failures have happened elsewhere? Are there new risks emerging with technology?
So, like, if a similar train had issues with metal fatigue in a similar climate somewhere else.
That failure mode must feed into your current safety assessment. It's a known hazard now.
Okay. Then moving inwards, you mentioned organizational requirements. Is this about whether the organization can actually handle the new thing?
It is, yeah.
Yeah.
Internal capability.
Yes.
Does the operator have the skilled staff, the training, the procedures to safely manage and maintain this new system for, say, the next 30 years?
Oh, good point.
If you bring in a super advanced signal system that needs a PhD to maintain it, and you only employ 2 such people, well, that workforce gap is a safety hazard right there. Needs a plan.
And this also includes the organization's own internal standards.
Yes, their own specific safety policies, which might actually be tougher than the minimum legal requirements.
Then we need to define the actual targets, the safety criteria.
Right. What are the specific safety goals for this project? What exactly are we trying to achieve? And, more technically, defining the acceptable limit of tolerability for risk.
That sounds like a tough conversation. How much risk is okay?
It is tough. It dictates how much residual risk is allowed after you've done everything as FAR. Often it's a numerical target, like an acceptable number of fatalities per million operating hours. Setting that limit up front is crucial and difficult.
And since humans run the railway, we absolutely need user integration. Human factors, HFI.
Could agree more. A technically perfect system can still be unsafe if people can't use or maintain it properly. You have to account for human requirements.
Like if a safety procedure is so complicated that staff find workarounds.
Exactly. If they bypass it to save time, then that safety control has effectively failed the SFAP test because of human factors. You have to design for the real human, warts and all.
Okay. And the final layer you mentioned was accreditation.
Yeah, the requirements from the accrediting body, the regulator, they often have very specific criteria, maybe about the type or quality of evidence they need to see.
Wow. Okay, so all of that, law history, internal rules, risk targets, human factors, regulator demands, all feeds into scoping out the SSA plan.
That's it. Without pulling all those threads together right at the start, your final safety argument is just incomplete. It won't stand up to scrutiny.
Right. So we've got the legal duty, SFA, RP. We've gathered all these complex inputs, scoped the project based on them. Now, how do you actually structure all this information into a solid, defensible argument?
Well, the SSA framework provides a pretty clear roadmap for the documents. It's usually a 3-level hierarchy.
It's like a pyramid structure.
Kind of. You can think of it like planning a big military operation. You've got your overall strategic doctrine, then your specific operational plan, and finally the evidence from the field.
Okay, I like that analogy. So, level 1, the top level.
That's the SSA guidance or procedure. This is the strategic level. It defines the whole organizational framework for safety assurance.
Answering the question, how does this organization generally manage safety for changes?
Exactly. It covers the high-level policy, the main responsibilities, the general process flow. Now, this is usually a baseline. It often gets tailored for specific types of projects.
Like, you might have one procedure for software changes and another for major track work.
Precisely. Or it might be adapted for one specific large program.
Okay, so level 2 gets more specific then. The System Safety Assurance Management Plan, SMP.
SMP, yeah. That's the operational plan. This document lays out how this specific project manages safety. It's the roadmap, the constitution, if you like, for safety on one particular change or project.
What's in it?
It details the specific methods they'll use, the schedule for all the safety activities, who's responsible for what on this project, and the structure for building up the final safety case as the project progresses.
Right, the detailed plan of attack for this specific mission.
You got it.
And level 3 is the culmination, the safety case and evidence.
This is the field report. The proof? It answers. How is safety actually demonstrated for this specific system?
So this is the structured argument itself.
Yes, backed up by all the objective evidence test results, analysis reports, sign-offs, everything proving that the system meets that SFAP standard. This is the document that gives confidence to everyone involved, the operator, the regulator, the public.
Now, you mentioned earlier this process isn't static. It's dynamic, iterative. Why is that iteration so vital?
It's absolutely crucial because safety is always dealing with reality, and reality changes as you learn more.
Meaning the assumptions you make early on might be wrong.
Exactly. The assumptions and the risk estimates you make way back in the concept phase, they're pretty abstract. As the design gets more detailed, you get real data, you build prototypes, you do tests, and that new information might completely change or invalidate your early assumptions.
So the SMP and the safety case can't just be written once and filed away.
No way. They have to be living documents, constantly updated. If your first risk assessment assumed, say, a manual shutdown takes 5 seconds, but then you test it in the field and find it actually takes 8 seconds under pressure, well, your whole safety argument based on that 5-second assumption needs to be reevaluated. Iteration is key.
And that iterative nature means safety has to be locked into requirements right from the start, all the way through V&V, verification, and validation.
Absolutely. You can't just bolt safety on at the end. Safety requirements have to drive the design choices.
How do the early SSA phases make sure that happens?
Well, first you have the concept design stage. That's where you identify the initial high-level safety considerations. If we're designing a new bridge, the concept immediately includes basic safety requirements about load limits, fatigue life, things like that.
Establishes the foundation.
Right. Then, after the concept, but before you dive into the really detailed design, you need the impact assessment.
What does that do?
It's like a critical checkpoint. It formally looks at the potential safety implications of the change you're proposing. Does this new system mess with an old system in a dangerous way? Does it introduce completely new ways things could fail?
And if it finds big problems.
It can actually force you back to the drawing board, back to the concept phase. This assessment is vital because its findings directly shape the scope for all the detailed safety work that follows, the stuff documented in the SNSMP.
So the SMP scoping uses that impact assessment output to set clear boundaries, define exactly what needs to be proven safe and how.
That's it. It sets the terms of engagement for proving safety. All before, as you said, a single nail is hammered or a line of code is written.
Okay, if the SNCP is the roadmap and the rulebook, then the hazard assessment process. That sounds like the real engine room.
That's a good way to put it, yeah. This is where the real heavy lifting happens, the core technical work.
Focus on finding and controlling every single hazard you could reasonably foresee.
Every single one associated with the change. And it involves a series of structured workshops, multidisciplinary teams getting together.
Right, and this is where we get that alphabet soup of acronyms you mentioned, PHA, SHA, SSHA, IHA.
Yeah, it can seem like that, but each one represents a different stage, a different focus, and the analysis gets more rigorous as the design gets more detailed.
Okay, let's try and break those down, maybe keeping our audience of engineering students in mind. Let's use an example. Say, a new type of automated door on a train carriage. Where do we start?
We start with PHA, preliminary hazard analysis.
Preliminary, so early on.
Very early. Concept phase, maybe early design, before you've picked all the specific components. For our automatic door, the PHA asks the broad questions. What kind of hazards could this technology introduce?
Like?
Pinching fingers, someone getting trapped, the doors opening or closing unexpectedly, maybe electrical shock from the mechanism. Broad categories.
And the PHA identifies these and suggests general controls.
Yeah, it identifies the hazard type and gives an initial rationale for a control, like the system needs some kind of obstruction detection.
Right.
And critically, it determines if you even need to do more detailed analysis on a particular hazard later. Some might be ruled out early.
Okay. Then as the design gets more concrete, we move to SHA and SSHA. System and subsystem hazard analysis.
Right. Now, SHA, system hazard analysis, looks at the whole integrated system.
The big picture for the doors.
Exactly. How does the entire door system, sensors, motors, control logic, power supply, fail as a complete unit? What happens if there's a total power loss? Can people still get out in an emergency? That's SHA territory, system-level failures.
Right, it's SSHA subsystem.
SSA drills down. It focuses on the individual bits, the smaller components. So for our door, the SHA might look specifically at the failure modes of the door motor itself, or the reliability of the pressure sensor used for obstruction detection, or the software logic in the local controller.
So SHA is the whole system failing. SSHA is one specific part failing.
That's a good way to think about it. SHA, the consequence of total brake failure. SSHA, the reliability of the brake fluid pressure sensor. Different levels of detail.
Got it. And then there's one you flagged as critical and often missed. IHA, Interface Hazard Analysis.
Yes. IHA, hugely important. This looks only at the joins, the seams, where different systems or subsystems connect and talk to each other.
Why is that so important?
Because that's where things often go wrong, especially with complex software. For our automated door, the IHA is vital. It has to look at the interface between the door's own control unit and the main train control management system, the TCMS.
What kind of problems could occur there?
Well, what if the TCMS sends a lock doors command at the exact moment the door controller senses an obstruction and is trying to open them? Which command wins? Does it freeze? Does it do something unpredictable? Interface failures are notorious. IHA forces you to analyze those specific communication handshakes.
Okay, that makes sense. Moving from finding hazards to proving reliability, we get to safety integrity level, SSA allocation. This sounds very technical.
It is quite technical, yes, but absolutely fundamental for engineers. SSL basically defines how dependable a safety function needs to be.
A safety function being something designed specifically to prevent or mitigate a hazard.
Exactly, like an emergency brake activation, or the system that detects obstructions for our door. SIL answers the question, given how bad the consequences are if this function fails, how reliable does it need to be?
And there's a scale, SIL 1 to 4.
Yes, 4 levels. SIL 1 is the least demanding, maybe for a simple warning light. SIL 4 is the absolute highest integrity level. That's reserved for functions where failure could be catastrophic.
Like
the core ATP system automatic train protection that prevents trains colliding head-on. A SIL 4 function needs an incredibly low probability of failing when it's needed, almost negligible.
So how do you decide if a function needs to be SI 1, 2, 3, or 4? It can't just be a gut feeling.
Oh, absolutely not. It's driven by risk analysis, purely quantitative.
How does that work?
First, you figure out the risk without that safety function in place, the unmitigated risk. What's the likelihood and consequence of the hazard if you do nothing?
Okay.
Then you compare that raw risk level against the tolerable risk target, that limited tolerability we talked about earlier, the level of risk society or the operator deems acceptable.
The gap between the raw risk and the acceptable risk.
Exactly. That gap tells you how much risk reduction you need from your safety function. And that required risk reduction factor maps directly, mathematically, onto a specific SIL level.
So if you need a massive risk reduction, you need a high SIL level.
Precisely. If the analysis shows you need to reduce the chance of a dangerous failure to less than, say, 1 in a billion per hour, that might demand a SIL 4 design. The SIL allocation translates SFIRP directly into a hard engineering specification for hardware or software reliability.
Right, so we've gone through the hazard analysis engine room, we've designed controls, maybe assigned SIL levels. Now, surely someone needs to check all this work independently.
Absolutely. That's where the requirement for external scrutiny comes in, and the main mechanism for that is the Independent Safety Assessment, or ISA.
ISA, independent being the key word there.
The absolute key word. The ISA is about forming an independent judgment. It has to be separate, completely separate from the team that designed the system, the team that built it, and the team that will eventually operate it.
Why is that independence so crucial? Why can't the design team, who know the system inside out, just check their own work?
Because the whole SSA process, remember, is driven by proving safety, SFRP, and that demands objective, unbiased verification. Self-interest, cognitive bias, they can creep in. Independence removes that.
So what are the ISA's main objectives? What are they actually checking?
It's pretty comprehensive. First, they need to confirm that the safety requirements themselves, the goals set at the start, were actually appropriate and adequate. Did they properly address the risks and the SFARP duty?
Okay, checking the foundation.
Then, they verify that the actual system, the hardware, the software, the civil works, even the operating and maintenance procedures, that everything actually complies with those requirements. Does it do what we said it needed to do?
Verification of compliance.
And perhaps most importantly, the ISC provides that third-party validation. It confirms the project meets recognized standards, industry standards, legal rules, regulatory demands. It shows the organization did its due diligence.
So the ISA isn't just kicking the tires to see if it works. They're checking the process used to build it, the requirements, the evidence, the whole argument.
That's exactly right. The hazard assessment work we just discussed that directly informs the ISA's brief, it tells them what areas need the deepest scrutiny.
And that leads to the ISA activities, audits, reviews.
Yep, audits, reviewing all the evidence documents, maybe interviewing key personnel. It all culminates in the final ISA report. That's the formal sign-off, saying an independent body has examined the safety case and found it to be sound and defensible.
Okay, that independent check sounds vital. Now, all this checking and assurance, it seems layered. Is there a structure to it?
Yes, there is. To manage all this scrutiny effectively, the SSA framework usually talks about 3 distinct levels of assurance. They're often separated by who's doing the checking and the level of risk involved.
3 levels. Let's break them down. Level 1.
Level 1 is design and build. This covers the activities done by the supplier or the contractor themselves, their internal checks.
Like the initial design reviews.
Exactly. Design reviews, doing analyses like FMEA failure mode and effects analysis, component testing, software unit testing. This is the team creating the system, doing their own initial checks and verification. It's the first layer.
Okay. Then level 2.
Level 2 is the assure level. This is where the independent assurance happens, usually initiated by the purchaser or the rail operator who's buying the system, or maybe by third-party specialists they appoint.
And this is where the ISA fits in.
Yes. The ISA is a core level 2 activity, but it also includes things like independent design checks, maybe specialist reviews of things like software integrity or human factors. Level 2 is essentially checking that the work done at level 1 was done properly, objectively, and meets the purchaser's needs. Assuring the assurance, if you like.
Assuring the assurance. I like that. Okay, and finally, level 3.
Level 3 is the accept level. This is where the ultimate responsibility lands. These are the final checks and due diligence done by the rail transport operator or whoever is formally accepting the asset onto their network.
This is the point they legally take ownership of the safety.
Precisely. Level 3 includes final handover checks, making absolutely sure all the operational staff are fully trained, confirming maintenance plans are ready, and critically, ensuring that robust configuration management processes are in place before that system goes live and starts carrying passengers or freight.
So 3 layers. Create and self-check, independently assure, and finally, formally accept responsibility.
That's the idea. A safety net with multiple layers of verification and responsibility.
We've worked through the process, the checks, the independent reviews, and it all leads to this final document, the safety case. This is the big one, right? The structured argument proving the system is safe, SFARP.
It is. It's not just a thick binder gathering dust. It's effectively the legal defense, the documented proof that the organization has met its duty of care.
So what are the key pieces, the essential components that make up a robust safety case?
Well, it's really a collection of critical documents that all have to tell a consistent story. First up, you usually have the Safety Assurance Report, or SAR.
Okay, the SAR, what does that cover?
The SAR summarizes the outcomes of all those assurance activities we've talked about, the reviews, the tests, the analyses, the ISA findings. It provides the explicit evidence showing that every safety control measure that was decided upon during the design phase has actually been put in place, tested, and shown to be effective.
It connects the plan to the reality.
Exactly. And intimately linked to the SAR is the hazard log.
Ah, yes, the log of all identified hazards.
It's more than just a list. It should be the living heartbeat of the project's safety story. It needs to be comprehensive, tracking every hazard identified right from the initial PHA and showing exactly how each one was treated. Was it eliminated, controlled, minimized, accepted with justification?
And it needs to be kept up to date throughout.
Absolutely. Continuously.
Yeah.
A hazard log with gaps, with hazards that don't show a clear closure or control measure in evidence, well, that's a massive hole in your safety argument, a huge red flag for any assessor.
Okay, so the SAR summarizes the activities. The hazard log tracks the hazards and controls. What provides the actual proof?
That's the control output data. This is the objective evidence itself, the raw material.
Like test reports, simulation results.
Exactly. Test reports, analysis models, calculations, compliance certificates for components, sign-offs on training procedures, maintenance instructions. It's all the tangible proof demonstrating that the controls are real, they've been implemented, and they work. This is what anchors the claims made in the SAR and hazard log. This shows SFARP was met in practice.
Now, building this argument, especially for really complex systems, Lots of software, lots of interactions, just writing pages and pages of text can get confusing, right? Hard to follow the logic.
It can, yes. Traditional narrative safety cases could become incredibly dense and, frankly, difficult to audit effectively. It was sometimes hard to see if a claim made on page 10 was actually supported by evidence listed on page 500.
Which led to new tools. You mentioned goal structuring notation, GSN.
Yes, GSN has become increasingly common, especially for complex or software-intensive systems. It's a major step forward, really. It provides a formal, graphical way to present the safety argument.
Graphical. So like a flow chart for safety.
Sort of, but more structured. Instead of dense paragraphs, GSN uses a standard set of symbols to create a visual map of the argument. It explicitly shows how a high-level safety claim, they call it a goal, is broken down and ultimately supported by concrete evidence called solutions.
That sounds much clearer. Easier to see the links and maybe easier to spot gaps.
That's exactly the point. It makes the structure transparent. Let me quickly outline the main symbols. You have goals, usually shown as a rectangle. This is your top-level claim, like the braking system will always stop the train within the safe distance.
Okay. The main safety objective.
Then, to show how you achieve that goal, you use a strategy, often a parallelogram symbol. This describes your approach. For example, we achieve this goal through redundant braking circuits and ensuring sufficient friction.
The method.
Then, supporting the strategy, you have the solutions, usually circles. This is the actual hard evidence. The brake test results, the friction calculations, the SIL assessment for the brake controller, the ISA report section on braking.
A proof point.
Right. And if a line pointing to a solution is missing, the GSN diagram makes that gap immediately obvious. You can see straight away that a part of the argument isn't backed up. Finally, you have context elements, often rounded rectangles, which state any assumptions or conditions that apply, like this argument assumes tire rail friction coefficients are within standard limits.
Wow. Okay, so GSN forces a very logical, traceable structure onto the safety argument, takes it away from just opinion.
Precisely. It moves safety justification towards formal, verifiable logic. Hugely valuable.
Now, the ultimate success of that argument, whether presented in GSN or text, relies on proving the system works as intended. This brings us to verification and validation, V and V. People often mix these up.
They do, all the time. Even experienced engineers sometimes use them interchangeably, but they are distinct and both are critical.
So what's the core difference?
The classic summary is verification asks, are we building the system right? Validation asks, are we building the right system?
Okay, unpack that a bit. Verification first. Are we building the system right?
Verification happens throughout the development lifecycle, at the end of each phase usually. It's about checking that the output of a phase meets the requirements that were set at the start of that same phase.
So checking against the immediate specification.
Exactly. For example, verifying that the detailed software design correctly implements the requirements laid out in the software specification document. Or verifying that a manufactured component meets the dimensions specified on the drawing. It's about internal consistency and conformity to the spec for that stage.
Okay. And validation. Are we building the right system?
Validation typically happens much later, usually just before the system is accepted and put into service. Often involves extensive real-world testing or trials. It's about checking that the final, complete system actually meets the end user's needs and fulfills its overall intended purpose, especially its safety requirements.
So it checks against the original problem or need.
Yes. For instance, we validate that the new train door system actually allows passengers to get on and off safely and efficiently in a busy station environment under various conditions. Does it solve the original problem? Does it meet the user's needs safely and effectively? Verification checks the drawings. Validation checks the finished product works in the real world.
That's a very clear distinction. Thanks. So once the system is verified, validated, accepted, level 3 complete, the project is done, but the safety job isn't over, is it?
Not by a long shot. Now you have to sustain that safety over maybe 30, 40, 50 years of operation. And that's where configuration management, CM, becomes absolutely essential.
Why CM? Because things change over time.
Constantly. Rail systems aren't static. Components wear out and get replaced, maybe with slightly different versions. Software gets patched and updated. Maintenance procedures get tweaked based on experience. CM provides the strict control, the governance over all these changes.
To make sure a small change doesn't accidentally break the safety case.
Exactly. You need to ensure that a seemingly minor update, a new sensor here, a software patch there, doesn't inadvertently undermine the assumptions or controls that the entire safety argument was built on years earlier. CM protects the integrity of the validated system baseline.
And how is that control actually managed? Is there a specific body?
Yes, typically through a configuration control board, or CCB.
The CCB. Sounds formal.
It needs to be.
Yeah.
The CCB acts as the guardian of the system's configuration baseline, and therefore its safety case. It's usually a multidisciplinary team.
Who sits on it?
You'd have a CCB chair, a dedicated configuration manager, systems engineers, technical experts from relevant fields like signaling, rolling stock, track, safety specialists, maybe people from procurement or logistics.
And their job is to review any proposed change.
Any proposed change to a baseline item, anything under configuration control. They review the change request, assess its potential impact, especially the safety impact, which might trigger a mini SSA process just for the change itself, and then they make a formal decision. Approve, reject, or maybe defer the change, pending more information.
I can see how engineers might find that bureaucratic sometimes, wanting to just fix something quickly.
It can feel that way, yes. But the CCB process is the essential gatekeeper that prevents uncontrolled changes from eroding the system's safety over its long operational life. It maintains the validity of that original SSA effort. #outro.
Okay, let's try and pull all of that together. We've covered a huge amount of ground. What really strikes me is the sheer scale, the complexity of system safety assurance. It's so much more than just a final check.
It really is. It's this comprehensive, integrated, and iterative framework, and it's all driven by that fundamental legal duty we started with, SFARP, applied right across the entire life cycle of any change.
It really shifts safety away from just being someone's opinion, doesn't it? Like, yeah, I reckon it's safe.
Absolutely. It forces safety to become evidence-based, documented, independently verified proof. It makes sure every technical choice, every SIL level, every control measure can be traced back to a logical argument that shows you've done everything reasonably practicable to minimize harm.
And for our listeners, the engineering students, the graduates just starting out in rail or related fields, the key takeaway is that this is your reality now.
It is. Whatever you design, whatever component you specify, whatever procedure you write eventually, it's going to be looked at through this SSA lens. From those early PHA workshops right through to the ISA, and then living under CCB control for decades.
So understanding this framework isn't just nice to know.
It's fundamental. It's essential for doing your job responsibly and effectively in the modern railway environment.
Now, thinking bigger picture, the SSA framework, as you said, is iterative. It learns from the past, adapts to new risks like cybersecurity. But looking ahead, this raises a pretty challenging question, doesn't it?
It does. A really profound one for the next generation of safety professionals. Well, SSA, as we've described it, is built on demonstrating safety using fixed evidence at particular points in time. Test reports from last month, design files signed off 6 months ago, V&V completed before launch.
Right, snapshots in time.
But what happens with the rapid rise of artificial intelligence? Machine learning. Autonomous systems that are designed specifically to learn and adapt continuously, maybe changing their own operating rules daily based on new data.
Yeah. How does that fit with fixed evidence?
Exactly. How will this fundamentally challenge the very nature of SSA? If the system itself is constantly evolving, what does evidence even look like? How can you satisfy SFARP and provide assurance for a system whose safety argument might, in theory, be changing hour by hour outside of these traditional V&V cycles?
That's a huge question. What kind of dynamic proof would even be acceptable?
That's the challenge.
Yeah.
That's the question that today's students and young engineers, you're listening now, will need to figure out as these technologies become reality on our railways. It's the next frontier for system safety assurance.